Hey guys, so in this video let's do some example problems that tend to seem really confusing but are really not that hard if you go through them step by step. So these problems, we're going to have concentric shells, a system of concentric shells, and we're going to be asked to find the electric field and the potential in different regions. So to start with, suppose that you have a charge Q that is surrounded by a conducting spherical shell. Okay, so this part is the conductor, and this is empty space here, and this is also empty space on the outside. Okay, so suppose that the inner radius is R1 and the outer radius is R2, and we're asked to find the electric field in the region R less than R1, R1 less than R less than R2, and R less than or R greater than R2. Okay, so for this region, when R is less than R1, we're here. So to find the electric field, we're going to draw our Gaussian surface. Okay, we know that the field pattern of Q is radially away, so we pick a sphere of radius R. Okay, and remember that Gauss's law says that E dot dA equals Q enclosed over epsilon naught. And then we've gone through and we found that the electric field for a point charge is kq over r squared. And then for this region, when you're inside the conductor, then we know that the electric field inside the conductor has to be 0. Okay, so how does the electric field suddenly become 0? Okay, it wasn't 0 here. Then, there were these electric field lines going out and then suddenly became 0. But what made that happen? So we know, okay, if you look at Gauss's law, okay, so and there's an integral sign here. So if you look at Gauss's law, you see that electric field can be 0 if the charge enclosed by the Gaussian surface is 0. Okay, so then for when we're inside the conductor, our Gaussian surface is going to be here. So if the Gaussian surface is enclosing 0 net charge, then the electric field can be 0. Okay, and then the way that can happen is that from this initially neutral conductor, some negative charge comes on the inside surface of this conductor. Okay, then this charge plus this minus charge is equal to 0, so the electric field becomes 0 in this region. Okay, what about R greater than R2? Or let's talk about this charge first. Okay, so if this conductor was initially neutral, some negative came in, then there's some positive floating around inside this conductor. And where's that gonna go? Conductor can only have charge on its surface. So that charge goes on the outer surface. So this outer surface has some charge Q on it. Okay, and then to find the electric field, you're gonna draw your Gaussian surface like this. Okay, and then the net charge that's enclosed by this Gaussian surface is the sum of all three of them, which is Q. So the electric field is going to be kq over r squared. Okay, because these two cancel each other. So this is the charge distribution and the electric fields in a different region for this configuration. Okay, so now let's take the same thing that we had just now. We had R2, our R1 and R2, and this conductor. Okay, but now suppose that this has some plus Q on it. Okay, and then we're asked the same thing, that find the electric field for R less than R1, R1 less than R2, and R greater than R2. And our R's are here. Here's R1. Okay, so these are supposed to be spheres. And this is R2. Then for R less than R1, we're here, so we're going to draw our Gaussian surface. Okay, and then the charge enclosed by this Gaussian surface is Q. So the electric field is going to end up being KQ over R squared again. Okay, and then for this, when you're here inside the conductor, the electric field has to be 0. Okay, so we can blindly say it's 0. But what about the charge distribution? What's going to be the charge on the inside of this conductor? It has to be something that cancels the charge that's in the middle, the point charge. Okay? And the way you can cancel this point charge is to have some negative equivalent charge. So the electric field in this region is going to be 0. Okay, so then in the previous problem, when some negative charge came in, there was some positive charge left floating on the outside, and that went on the outside. Okay, but in this problem, we also had some charge to begin with. Then where is that going to go? It's also going to go on the outside. So the outside is going to have a net charge of plus 2q. Okay, because some negative charge came on the inside, which left an equivalent positive q left floating around. And then there was this positive q that has to go somewhere, and it can only go on the outer surface because the inner surface is forcing the net charge to be 0, so the electric field inside the conductor is 0. Okay, so this charge, moves outside, and the total charge on the outside becomes 2q. So then if you're finding the electric field for R greater than R2, you're going to draw your Gaussian surface like this. Really bad. And then you're gonna have to find a net charge, which is this plus this plus this, which is 2q. So the electric field is going to be k times 2q over R squared. Okay, so if there's any net charge on the conductor to start with, just send it on the outside. Okay, that's a good rule, or you can just think about it like this. Either way. Okay, so now let's suppose that you have this configuration and your charge is enclosed by two concentric spherical shells. And, same thing. So this is R1, this is R2, R3, and R4. And we have to find the electric field in all the different regions. Okay, so this is empty space, and this is a conductor, then this again is empty space here, then this is a conductor, and then this here is empty space again. Okay, so we have to find the electric field for R less than R1, R1 less than R less than R2, R2 less than R less than R3, and R3 less than R less than R4, and R greater than R4. Okay, so we know that for this region, when R1 is less than R2 is less than R less than R2, then the electric field is 0. Okay, we don't even have to do anything. We already know it's 0 here. And then also in this region, the electric field has to be 0. Okay, because that's this region. Okay, what about the other regions? We know that when you're on the inside, when R is less than R1, you're going to draw your Gaussian surface like this. And then the charge enclosed by the Gaussian surface is Q. So the electric field is KQ over R squared. Then the way this the electric field inside this conductor becomes 0 is some negative charge comes on the inner surface from this initially neutral conductor. Okay, then since some negative Q came in, then there's some positive Q left over, which goes on the outside. Okay, so the outside has plus Q. So that implies that in this region, the charge enclosed by this Gaussian surface is going to be Q minus Q plus Q, which is Q. So the electric field would be KQ over R squared. Okay, then how does the electric field become zero in this region? There has to be a net charge of zero enclosed by the Gaussian surface. Okay, so your Gaussian surface is going to be here. Okay, then it needs to see a net charge of zero. Right now, there's this Q, and there's this minus Q, and there's this plus Q. So this plus Q has to disappear somehow. So some minus Q comes on the inside from this initially neutral conductor. So this is minus Q. So now the net charge seen by this Gaussian surface is zero. So it makes sense that the electric field is zero. Okay, then since some negative Q came on the inside, there's some positive Q floating around, and that goes on the outside. Okay, so then to find the electric field for R greater than R4, draw your Gaussian surface. Then the charge seen by this Gaussian surface is Q minus Q plus Q minus Q plus Q, which is Q. Okay, so the electric field would be KQ over R squared. Okay, now suppose there was some Q on this outer conductor to start with. Then what difference would it make in this problem? Okay, everything is going to stay the same up to the point where R is greater than R4, because any excess charge on the conductor you can send on the outside of the surface. Okay, so then if it had some Q on it, then that Q just goes on the outside, and then you would factor another, whatever charge was that it initially had inside it in the charge that's on the outer conductor. Okay, that's all you do. Whether it's positive or negative, just send it on the outside, and that's the only thing that changes in this problem. And another way to think about it is, suppose you had this plus Q on this conductor to start with, then just forget about it for a second. Then if some negative Q goes on the inside, then you have to then there's some positive Q left over. Okay, which goes on the outside, and then there's also this plus Q which has nowhere to go, so it just goes on the outside because that's the only place that it can go to by default. Okay, so basically just send your excess charge on the outside of a conductor. So that's how you handle these problems for the electric field. Okay, now let's look at the same scenarios, except let's find the potential in the different regions. Okay, so first let's look at the case of point charge instead of or inside of a conducting shell. So this is R1 and this is R2. And suppose you have to find the potential at point A, at point B, at point C, and D, and point E. Okay, so remember that potential produced by a conducting shell, if R is less than R, then the potential is kq over the radius of the shell, and for R greater than R, potential is equal to kq over however far you are from the center of the sphere, the conducting sphere. Okay, so this is true for conductors. It won't be true for insulators. So if and for a point charge, we also know that the potential is just kq over R. Okay, so at point A, so here's your R. Your R is going to be this distance. Oops. R. And to find the potential at A, it's going to be the contribution of this point charge, the charge on this inner sphere, and this outer sphere of the cylinder. Okay, so we know that the charge on the inner sphere is going to be it's going to be negative q. So we're going to have a charge of negative q here and a charge of plus q on the outside. Okay, so for point A, you're inside both this conductor, inner conductor, and the outer conductor. Okay, so your potential is going to be at A is going to be the contribution of the point charge, which is kq over R, plus the contribution of the inner shell, which is going to be k times negative q over R1, and the contribution of the outer shell, which is going to be kq over R2. Okay, so we use capital R's here because these are the radii of the shells, and since we're inside these shells, we have to use the capital R. Okay, what about potential at B? Okay, so let's call it the radius to point A, RA. Then at B, oops. So it's going to be a different R, RB. So what's different between these two scenarios? Okay, you're still inside these two shells, and you're going to have the contribution of this point charge. So it's going to be exactly the same thing. Plus ditto, plus ditto. Okay, same thing. And this is potential at B. Okay, what about the potential at C? Okay, now at C, you're outside this inner shell, but you're still inside this outer shell. Okay, so you're going to have the contribution of this point charge, that is going to be kq over RC plus k times negative q over RC. Okay, and RC is being measured from the center to C. Okay, so now we use little r because you're outside this this shell, and then plus kq over R2. Okay, what about the potential at D? So it's going to be the contribution of the point charge, kq over RD, plus k times negative q over RD, because again you're outside, plus kq over capital R2 because you're still inside the outer shell. Okay, what about potential at E? Now you're outside everything. Okay, so you're going to have the contribution of the point charge, kq over RE, plus contribution of this one, it's going to be k times negative q over RE, plus kq over re. Okay, so and you're going to use small r's for all of them. And these two cancel, you see, and you're only going to be left with this term, but but really the contribution of all of them is here. Okay, and then suppose you wanted to find the work done in going from point B to point E. Suppose you move a charge Q from point B to E. What you would do is you would find the potential difference between B and E. So you'd take this VE and then you would do minus VB. So you would do, so if you want to find the work in going from E to B or B to E, so that would be whatever charge that you're moving times V E minus VB. Okay, so this is your potential difference, and potential difference times Q would give you the work done. Okay, so now let's do another example. Suppose you have Q here, and then you have your two spherical shells. Here's your R1 and here's your R2. And this time let's put a negative 3Q on this one. Okay, on this shell. And then same thing, let's find the potential at different points. So let's find the potential at this point. Oops, Control C. This point, say A. This point B. This point and this point, okay, C. Okay, so what is going to be the charge distribution on the surface of the shells? Okay, there's Q here, and then we know that electric field inside this conductor has to be 0, and so then there has to be a charge of minus Q on the inside of this sphere. Okay, then if some minus Q came here, then you send this minus 3Q outside, and then if some minus Q came here, then there was some plus Q floating around, which also goes on the outside, so the outside is going to have negative 2Q on it. Okay, another way you can think about it is if this one had negative 3Q and some minus Q went here, then what you're left with is minus 2Q. Okay, well, whichever way you like to think about it. So okay, so potential at A is going to be KQ over RA. Okay, where RA is this distance. Okay, plus the contribution of the inner conductor, which is going to be K times negative Q over R1, and the contribution of the outer conductor, which is going to be K times negative 2Q over R2. Okay, potential at B is going to be KQ over RB. Okay, RB is this distance plus KQ over, or K negative Q over, now it's going to be small rb because you're outside this inner shell, and then plus K times negative 2Q over R2, capital R2, and then potential at C is going to be, now you're outside everything, so it becomes KQ over RB plus K times negative Q over RB plus K times negative 2Q over RB. Okay, so same thing here. Suppose you want to find the work done in going from C to A, say, then that would be whatever charge you're moving between them times VA, or let's see, final is going to be A, initial is going to be C, and this would be a potential difference, and this would give you the work in moving the charge. Suppose you're given this configuration, and so now we have a charge in the middle, and there's a net charge Q on this shell, and the net charge of -3Q on this shell. And suppose you have to find the potential at point A and B, C, D, and E. Okay, so first let's talk about the charge distribution. So we know that there's a Q here, so then there has to be a minus Q here to make the electric field inside this conductor 0. Okay, so then what does this charge do? It goes on the outside. Okay, so on the outside of this inner sphere or outer sphere, you're going to have a charge of 2Q. Okay, so this one goes on the outside. Then let's see, so you have Q here, minus Q here, and 2Q here. So then this makes a total of 2Q. So then that implies that on the inside of this has to have a charge of -2Q. Okay, because that's the only way that the net charge inside this Gaussian surface that you would draw inside this conducting shell is going to be 0. Okay, so if some -2Q comes inside and it has some -3Q to start with, then what happens to the leftover -Q? It goes on the outside. So on the outside, the charge would be -Q. Okay, another way to think about it would have been, just directly send the -3Q on the outside. Then if -2Q comes in, then there's some +2Q floating around. And then -3Q plus 2Q would make -Q. Okay, so that would have given you the same thing. So now let's find the potential at point A. So you're going to have the contribution of this point charge that's in the middle. So that's going to be KQ over RA, plus the contribution of this inner sphere, which is going to be K times -Q over capital R1, plus then the contribution of this 2Q, K times 2Q over R2, okay, plus the contribution of this one, the inner surface of the larger shell, is going to be K times -2Q over R3, plus the outermost is going to be K times -Q over R4. Okay, so and then potential at point B is going to be KQ over RB. Okay, Q is the point charge in the middle, plus K times -Q over RB, which is the charge on the inner sphere. Okay, so for both of these we have to use small r's, because now you're outside this inner sphere, and then the rest of it is going to be the same as above for VA. Okay, the 2Q, you're inside it, so you're going to use capital R2, and same thing for the outer two shells. Then potential at C. Okay, at C, the point charge is going to produce KQ over RC, and the inner sphere is going to produce K times -Q over RC. And now you're outside this shell also, so the contribution of that one is going to be K times 2Q over RC also. Okay, and then the rest of it stays the same as above. Okay, potential at D is going to be, now you're outside this one, and this one, and you're inside this one. So it becomes KQ over RD plus K times -Q over RD plus K times 2Q over RD. Okay, so 2Q was this one, And now you're outside this one also, so that becomes K times negative 2Q over RD plus K times negative Q over R4, because you're inside that. Interesting, right? So since you're inside the conducting shell, we know that the potential inside a conductor is constant. So all these, R terms cancel out, and you're only left with this constant term. And same thing happened here at B. These R terms canceled out, and we were only left with the capital R terms, which imply that that the potential is zero regardless of what your R is in that region. Okay, and then finally at E, what's gonna happen is let's just do it here. Potential at E is going to be KQ over RE plus K times negative Q over RE plus K times 2Q over RE plus K times negative 2Q over RE. So all these terms cancel anyways. The negative 2Q is this one, and then you're left with the negative Q that's on the very outside, so this becomes plus K times negative Q over RE. So this is the only term that survives. Okay, so that's how you'd find the potential at different regions. And then same thing if you were to find the work in moving a charge from any of these points to another point, then you would find the potential difference times the charge, and that would give you the work done. Okay, so that's it for these problems. Next video is going to be about capacitors. See you then.